Uh, Mark, should we start now?
I am ready.
Okay. So I make a short introduction. Today, we are very glad to have a Professor Marc Roussel from the Aborted RNA Research and Training Institute, Department of Chemistry and Biochemistry, University of Lethbridge, Canada. And he will give you a two lecture on the dynamics of a huge network. The first lecture is today, and the title is Graphical Theoretical Stability Analysis, Part 1, the bridge between the network structure and the dynamics. So let's welcome Professor Russell.
Thank you. So I'm really delighted to give this lecture. I discovered the work of my gracious host just very recently, and it seems like we're thinking about a lot of similar things. So you're going to hear today about some work that we started actually quite a long time ago, and you'll see some of the dates on the papers. They're quite old. With Maya Mincheva, who was a postdoc with me at the time and has become a valued colleague since. I'll start with, let's see. There we go. All right, so I'll start with probably a burning question. Where is Lethbridge exactly? We're in the south of Alberta. For those of you who remember the Calgary Olympics, we're about 220 kilometers southeast of Calgary. So we're on the prairies within sight of the mountains. It's a lovely spot, but a place with very odd weather at times. This is the University of Lethbridge. We work in this lovely new building that opened in 2019. We were barely moved into it when the pandemic hit and we were all sent home. Our offices in the biotheory group are on the other side of the building, yeah, it's an interesting building. This was the university's first building, was this quarter-mile long thing that sits across these geological features we call coulees. So it's a very interesting place to work. We look out our windows and see wildlife, deer all the time. It's quite a lot of fun. So let's talk about the problem. So problems in models in cell biology and biochemistry are often really large. Dozens, if not more, chemical species, as many or more chemical reactions. They're really quite large, and these are considered small models in some ways. There are some models that are hundreds of species and correspondingly large number of chemical reactions. Very few parameters are available from the literature. When you try to parameterize even the simplest looking model, you often find that you run into roadblocks in terms of being able to find rate constants, concentrations, and so on. And when you do find parameters, you have to be careful because they're not transferable across species. And they're often not even transferable within an organism from different tissues. So you often have, for example, enzyme isoforms in different parts of your body that have different catalytic parameters. So you're constantly dealing with models where you don't know many of the parameters, and even the ones you do, there's great uncertainty around them. So, what sorts of things are we interested in? I'm a dynamicist. I started out my career working in nonlinear dynamics. And so I'm interested in things that have interesting dynamics, as I think many of you here are. And there's a lot of dynamics in biological systems. We have some cell and developmental events that are associated with clocks, so oscillators. The circadian oscillator, of course, is a very famous example, but there's also some more subtle examples like somatogenesis. So the somites, if you want to think of them this way, they're kind of like early developmental segments that'll develop into things like your vertebrae. And they are generated by a kind of a combination of a clock and then advective motion of the tissue as it grows. Multiple cell fates from a single genome is an example of what, the group that I'm talking to now, I'm sure would tend to think of as multi-stability. So, what the biologists call totipotency or pluripotency, these are all examples of multi-stability. We often get waves, especially during development, and they often result from bistability. And there's a really interesting example that Hello?
是
So I see a hand
那
up.
个
I'm
季
here.
季小姐吗？不好意思啊，我最近可能我不是确定说我到底有没有确诊这样子，所以嘿，对
蔡老师，你需要unmute。
所以我怕如果我不想给你的话，
蔡老师
我就不好意思啊。嘿，
，I'm
好，
sorry。
Is everything okay?
yeah, yes,
Okay. I'm hearing people talking to
You
each other and there's
you
a
have
hand up,
unmute。
so I
你
beg your
你
pardon?
把自己声音关掉。
I didn't quite hear that.
I think we are doing fine.
When you are
Please go
talking
ahead.
to somebody else, you need to mute yourself first.
Shall I continue?
yes.
Okay, all right.
Yes,
Okay.
please. Yes, please.
Okay, all right, yeah. So there's a really lovely example of wave dynamics that's important in cell polarization that Leah Edelstein-Keshet has been studying, which is this wave pinning phenomenon where basically stoichiometry determines how far a wave will travel. And of course, you know, Turing instabilities are often invoked as explanations for developmental patterning. Animal coat patterns are a famous example. We've been working on left-right asymmetry of internal organs, which at least one group believes to be due to Turing patterning, although that's still controversial. And I'll talk about that a little bit more later. So the general question we want to address is then what network features give rise to these dynamics? Because maybe if we look at network structure, at network features, we can worry a little bit less about parameters, this problem with parameters I was talking about earlier. Our work situates itself within a long tradition of qualitative stability analysis. There are lots of methods and a long history going back at least to 1965, and I've just listed a few papers here. There's many, 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 many more, including the work of your colleagues. We come from a particular tradition of using graph-based methods. There have been, again, lots and lots of those, and I'm listing maybe a few more here than I did of the other type, basically because this is a little bit more kind of what we think about when we're thinking about these qualitative stability analysis methods. So I mentioned Maya earlier. Maya's at Northern Illinois University. She's an associate professor, I believe now. We come from this tradition that goes back to Bruce Clark at the University of Alberta, came through Ivanova, who wrote a couple of papers, not a whole lot, a handful of papers, 2 or 3 papers on this, developing a slightly different twist on Clark's method that was much simpler. And then it kind of, there was a little bit of work applying it and trying to popularize it by some Russian groups, notably Goldstein, but it kind of lay dormant for a long time until we came back to it in the 2006, 2007 period. And since then, there's been a few developments, mostly led by Maya, I should say. So the Ivanova family of methods applies to mass action systems. Now, we can do things for non-mass actions models as well, but the kind of the nicest version of the theory works with mass action models. Roughly speaking, what you do is you build a bipartite graph of the reaction network, and I'll explain what that means in a few minutes. And you look for specific structures that we know to be associated with instabilities. What we end up with is a single, simple, necessary condition for saddle node bifurcation, so multi-stability. We get a similarly simple condition for Turing bifurcations. The case of Andronov-Hopf bifurcations leading to oscillations is a little more complicated. There are 2 cases. One is simple, and I'll talk about this one, and the other I will mention, but it's much more complex and difficult to apply, and at some point, we don't have software that does it yet. At some point, we'll have to develop some software for that. Okay, so this bipartite graph I mentioned, what does it look like? So what I'm showing you here is one of the simplest chemical oscillators, just as a kind of a simple pedagogical example. It's the Brussellator, which I'm sure many of you have heard of. And these 4 simple chemical reactions give you oscillations. And in the appropriate regime, if you add diffusion, you get Turing patterns out of them. So the bipartite graph, essentially what we do is we have species nodes, which I represent usually by circles, and we have reaction nodes, which I represent by squares. So in this particular example, we have 2 chemical species, X and Y. We have 4 reactions, and then arrows will point from a reactant to a reaction and then to the product. And if you have a reaction like reaction 3 that has 2 reactants, you'll get arrows from both reactants and then an arrow back to the product. If there are stoichiometric coefficients that are different from 1, we write them down as weights on the edges. And so there's a simple one-to-one correspondence between bipartite graphs and reaction mechanisms of the style that chemists or biochemists would be used to. Okay, so why do we care? So there are subsets of the bipartite graph known as fragments that I'll describe in slightly more detail in a few minutes that have a one-to-one correspondence with terms in the characteristic polynomial. So in other words, if you can find the fragments, you know exactly what the characteristic polynomial will look like. So a fragment consists of k distinct chemical species and k reactions. The reactions may not all be different from each other, so you can have repeated reactions, but the chemical species are all distinct. And so a fragment of what we call order k, so with k chemical species, corresponds to one of the terms that appears in the coefficient of lambda to the n minus k, where lambda is your eigenvalue of your characteristic equation. So if my characteristic equation looks like this, an would be the constant term at the end. So a particular fragment of order k, which has k distinct chemical species and k reactions not necessarily distinct, would correspond to a term that looks like this in the characteristic polynomial. So, and again, this is the thing that's special about mass action, is take the derivative of a monomial has a particularly simple form. And if you think about taking the derivative of x to the n, you get x to the n minus 1, right? So that's like taking x to the n and dividing by x. So if you take your rates, the rates corresponding to these reactions, and you divide them by the concentrations that are in your that are of the species that are in your fragment, then you'll get a term like this in your characteristic polynomial. And then there's this coefficient, which I'm calling ksk eta. The k denotes the little k denotes the order, so how many chemical species there are, and the eta is just because there'll be a bunch of these in general, so you have to number them. Okay, so fragments. So there's kind of a pyramid of concepts, if you will. So fragments are unions of subgraphs, and the subgraphs are unions of cycles and reactant to reaction edges. Okay, so the edges that go from reactions to products don't appear in the edge graphs, but they will, of course, appear in cycles. And the idea is that in a cycle or in an edge that you're going to include in a subgraph, each chemical species appears at the origin of only one edge. So you're always going to have an arrow going from any particular one arrow going from any given chemical species to a reaction, but you're never going to have 2 arrows coming out of one chemical species in a subgraph that belongs to a fragment. The cycles are really important, so let's talk about them a little more. The cycle is made up of what we call paths. Well, actually, this was a Bonobus terminology way back when. And there's 2 kinds of paths. There's positive paths, so xi going to a reaction, vk going to a product, xj. We denote these when we have to write down kind of what's contained in a fragment. We write down a path this way, just as with square brackets. And what a positive path does is it encodes a reactant to product relationship, right? We have a reactant, we go to a reaction, we go to a product. So that's what a positive path encodes. We also have negative paths, and in a negative path, we have 2 chemical species that point to the same reaction. So now if you think about what's going on here, is these are 2 reactants in the same reaction. And so the negative path encodes a co-reactant relationship, and we denote the negative paths just by putting a bar over the list of things in it. if you ever tried this theory, there are a few things that are a bit mind-boggling. So one of them is that xi vk xj is a different negative path than xj vk xi. And as a result, if you take those two negative paths together, that's a little cycle. So every time you have a negative path, you have the potential that there's a little negative cycle that just consists of going back and forth through that negative path. Cycles then can be classified into positive cycles and negative cycles. So a positive cycle has an even number of negative paths, and a negative cycle has an odd number. And if you've looked at some of the literature, whether it's one of his methods and the stuff we've done, or you look at some of the stuff that Feinberg has worked on, quite often you end up with positive cycles and negative cycles that have a definition that's a little bit like this. So this is a feature of many of these graphical methods, whether it's ours or somebody else's. Okay, so how do you calculate the coefficient of a fragment? And it's not that I want you to remember these formulas, but it's important to kind of think about the ingredients and how they work together. So if we want to, so the coefficient of a fragment is a sum of coefficients of subgraphs. So that now we've got to know how to calculate the coefficient of a subgraph. So if we've got if we encode a reaction this way as a sum of some stoichiometric coefficients times some chemical species making other maybe the same or different chemical species with some stoichiometric coefficients. So the alphas are stoichiometric coefficients of reactants and the betas of products. The coefficient of a subgraph, well, the subgraph can include edges. And for the edges, you just square the stoichiometric coefficient, you multiply all of those together. And it can include cycles. So cycles have another formula again. So for every cycle, what we're going to do is we're going to carry out these products and then throw a negative sign in front of that. So this is a product over negative edges, over negative paths. So this is a product over negative paths of the stoichiometric coefficients of the two reactants. So remember, a negative path encodes a co-reactant relationship, and there's a negative sign here. And so we multiply all of these together for all the negative paths, and then for the positive paths, we just multiply the stoichiometric coefficients of the reactant and product involved in that path. Now, if you think about this for a second, we were talking about positive and negative cycles a second ago. A positive cycle, because it's got an even number of negative paths, this is going to be positive, and then overall it's going to have a negative coefficient. And a negative cycle, because this will be now, there'll be an odd number of terms in this product, you'll get a negative sign from here, cancel this negative sign. So Kc will be positive for a negative cycle. So it's a little bit backwards from perhaps what you would like it to be. So if you end up with a negative coefficient for a fragment, we say that fragment is critical. And if you then think about what I was just saying about cycles, right? So you've got to add up these coefficients for subgraphs. That involves a product over, this is always positive, obviously. That involves a product over coefficients of cycles. And the negative cycles are going to contribute a positive value, but the positive cycles will contribute a negative value. And so what you have to have a critical fragment is at least one subgraph with an odd number of positive paths, of positive cycles, sorry. If you have an even number of positive cycles, their negative signs will cancel. So you need an odd number of positive cycles. So 1, 3, 5, whatever it turns out to be. So that's a necessary but not sufficient condition, obviously. So this all leads us to some theorems that I won't discuss the proofs. They're interesting. They're in our papers. They're kind of fun to look at. But just from the point of view of somebody who wants to use this theory, there's some theorems that are fairly easy to apply that fall out of this. So the first one, so n if n is the number of independent chemical species, so the number of chemical species you have after you've removed any mass conservation relationships, then a critical fragment of order n is a necessary condition for a saddle node bifurcation. Now, if you think back to the correspondence between fragments and coefficients of the characteristic polynomial, What this is basically saying is you need at least one. So in AN, what I was calling AN when I wrote the characteristic polynomial, that last term has to have at least one negative term in it if there's any chance for it to pass through 0, which is the condition for a saddle node bifurcation. So note it's a necessary condition. It's not sufficient. It's actually quite difficult to find. We don't have sufficient conditions yet. I'd love to get some, but right now what we have is necessary conditions. There's all kinds of little, things that can go wrong, and in my experience, often they go wrong in really small toy models, but in big models they don't happen. It's one of those things, right? But essentially, if you find a critical fragment of order n, there's a chance at least that you have a saddle node bifurcation and therefore bistability, right? One of the things we didn't talk about in our paper, but I know is of interest to some of you here is, of course, the last coefficient of the characteristic polynomial passing through 0, the constant term in the characteristic, that is not unique to saddle nodes, right? You also have transcritical bifurcations and pitchfork bifurcations that can be obtained through the passage of that coefficient through 0, because they're essentially degenerate saddle nodes. And we haven't worked out conditions to exclude those two cases, but it shouldn't be too hard. Okay, so another theorem. So now what if I have a smaller critical fragment of order k less than n? Well, that's a necessary condition for an Andronov-Hopf bifurcation due to positive feedback specifically. And these two theorems are found in this paper right here in Journal of Mathematical Biology. Okay, now it turns out a critical fragment is also a necessary condition for a Turing bifurcation. So if you're going to have a Turing bifurcation, you have to have a critical fragment, and that was kind of because of the way these things go, that was published a little bit out of order. It was published before the paper that laid out the basic theory in GMAT Bio. All right, so we have these three nice theorems. So here's a really simple example. This is the brusellator. So, oh, right, I had introduced the brusellator earlier, right? So it's a fairly simple model that oscillates. What is the critical fragment in the oscillator? There's exactly one of them. And it's this autocatalytic step. No great surprise, right? The autocatalytic step was put in there in order for it to oscillate. The coefficient of that fragment is -2. The characteristic polynomial of the brusellator, if you write it down and if you express the various terms in your Jacobian, just as, V over a concentration, it looks like this. Evaluated, of course, these things must be evaluated at the steady state. And you'll note here, here's my fragment. It involves V3 and X. You get a term in V3 over X in your characteristic polynomial. It's a fragment of order 1, so it's the coefficient of lambda to the 2 minus 1, which is 1. And the numerical coefficient here is exactly this coefficient from the critical fragment. And so there's this lovely one-to-one relationship. And of course, if you didn't have this, this is a simple second-order polynomial. If you didn't have this negative term, you could not make that system unstable in any way, shape, or form, right? That negative term is essential. And so that's the gist of how this stuff works. Now, of course, this is a very simple example, right? So I mentioned the theorem that said you get an Andronov-Hopf bifurcation provided you have a critical, so you get an Andronov-Hopf bifurcation due to positive feedback provided you have a critical fragment. Well, what about oscillations due to negative feedback? That case turns out to be a lot harder. So, and roughly speaking, all of this theory is actually built in the background on top of the Routh-Hurwitz criterion. And the critical fragments correspond to a single Hurwitz matrix having a negative determinant. The case of negative feedback, what you have to do is you have to look at interactions between pairs of Hurwitz matrices, and so it is more complicated. You have to find two positive fragments of order k plus 1 and k minus 2 satisfying a complicated condition. So you can already see there's going to be you know, there's going to be limits on, you have to have a certain size of system before this is even possible. And a necessary but very far from sufficient condition is that one of the pair of fragments contains a cycle of order 3 or more. So you're starting to look for, you know, kind of larger cycles in models and looking at these interactions between fragments. And I should have had a reference here. So there should have been a reference here to Maya's paper where she proved this. This is something she did years after she left my group. Okay, so let's talk about a more interesting application. We're in my group, we're kind of mathematical biologists. I trained as a chemist, but we have a very diverse group, people with different backgrounds. And Catherine Roussel here, and she's my wife too. But anyway, she works with me on a bunch of projects. So one of the projects we have been working on that we kind of had to park during the pandemic for a bunch of reasons is understanding the system that regulates left-right asymmetry of internal organs. So this is one of those things we all kind of know, but we don't think about super hard. So on the outside, we're very, very symmetric. But of course, on the inside, our organs are arranged very asymmetrically, and it's very reproducible, right? There's relatively few people whose internal symmetry is perfectly reversed. Almost everybody has the heart leaning over towards the left. The right lung's a bit larger than the left lung, and so on, right? So all our organs are arranged in a very specific way. People who have an inverted internal symmetry often have birth defects, because in fact that only happens if something went kind of wrong. If they're lucky, everything developed normally, but it's actually unusual. In fact, it's hard to estimate because there's only so much data that people have collected on this, but it's believed that the vast majority of fetuses with inverted internal symmetry never go to term. So it's an interesting system. I'll walk you through a little bit of the biochemistry here. There's two key chemicals here called lefty and nodal. So I'm using an L for lefty and N for nodal, and the little E's are external. So these are two proteins from the TGF beta family, and they bind to cell surface receptors. Nodal is the interesting one. It's the one that does something. So what nodal does is it binds to these cell surface receptors, and it activates a kinase domain on the inside of the cell, which phosphorylates SMAD2. SMAD2, you take a couple of those and then another protein called SMAD4, and they form a complex. There's several other proteins involved in this, but these seem to be the key ones. These things get transported into the nucleus, and once in the nucleus, they're part of a transcription factor that allows several genes to be transcribed. So I'm showing an inactive gene here with nothing bound, and then an active gene with this transcription factor, or at least I'm showing part of the transcription factor bound. SMAD2 and SMAD4 are conserved. So once they, there's a mechanism that causes them to be disassembled. And so there's a kind of a dynamic steady state between making this transcription factor, bringing it into the nucleus, and then disassembling it and sending it back into the site, sending the parts back into the cytoplasm. So things get exported back into the cytoplasm. Okay, so that's what nodal does. What about lefty? So lefty actually gums things up. What lefty does is it binds the same receptor, but it prevents it from binding nodal, and so it stops nodal from doing its thing. So lefty was called that originally because it was found on the left side of the embryo. And people thought, aha, that must be the thing that makes the left-hand side. Turns out nodal is the thing that makes the left-hand side, and the reason people didn't want to think about that too hard at the time, essentially is that nodal does a whole lot of things in the cell. And so, this was just one more thing that nodal is overloaded with in terms of its function. So nodal is the thing that determines the left-hand side at a particular moment in developmental time, and for a period of time after that. and then other mechanisms kind of take over. Nodal does a bunch of other things, but lefty is an antagonist of nodal. So I mentioned that, some genes get transcribed once nodal binds. Well, the two of the genes that prominently do are nodal. So there's an autocatalytic loop there, and lefty. So there's autoinhibition as well. And when people saw that, they thought, aha, I have an activator and an inhibitor. Maybe it's a Turing type of mechanism that's operating. So, so we basically built a little mathematical model of that. I say little, it's got, it is little by the standards of these kinds of things. 18 chemical species. There's 5 conservation relations because you have things like SMAD2 and SMAD4 that are conserved. Also the cell surface receptors, we didn't really take recycling into account. It didn't seem necessary. We have production and destruction of nodal and lefty. And so we started looking at that. Okay, so this model turns out to, if you just study the ODE model, so node diffusion, which is where we started because it seemed like, kind of start with the basics. It's a model with bistability. And I'm showing here one of many bifurcation diagrams you could draw. So the rate constant that I'm varying here is one associated with leaky expression of nodal. That was an interesting thing because you always have to worry about the fact that control of gene expression is not perfect. So, kind of how robust is this thing to some leaky expression of nodal? Because normally you would only want nodal to be made when that SMAD2, SMAD4 complex is bound to the promoter or the gene, the promoter for nodal. And so we end up with 2 stable steady states. You can think of this one here with a low nodal concentration as the right-hand side state, and then up here the high nodal concentration is left. And if you overexpress nodal everywhere, this steady state dies and everything is left side, which is what the experiments also tell us when they overexpress nodal. So it's bistable, so that's nice. So where is the bistability coming from? So the smallest critical fragment, okay, so not order n. So remember, n is 13 in this model. The smallest critical fragment is this, and it's probably, I'm not going to say you could have guessed this, but it's not surprising. So let's start here. So we've got nodal. It's binding to its receptor and it's forming the active receptor. The active receptor, this is Michaelis-Menten kinetics here, where it's phosphorylating SMAD2. So it makes SMAD2 or phosphorylated SMAD2. Then that turns 2 of these get together and make a dimer. The dimer gives you, then gets involved with SMAD4 and makes a transcription factor. And then this transcription factor goes and binds the gene and activates the gene, and that makes nodal. So, like I said, maybe not a real surprising circuit. So, so as I was saying, this is a critical fragment with a K that's much smaller than N, and is 13 in this model. There's 13 independent concentrations, and K is only 7. So what that tells you, strictly speaking, is you should have an Andronov-Hopf bifurcation. Which, turns out that if you look around hard enough, you can find Andronov-Hopf bifurcations in this model. But what this basically told us was that, well, it doesn't seem like lefty is necessary at all. So remember, the original hypothesis was that this is an activator-inhibitor system with nodal as the activator, lefty as the inhibitor, right? And then with the usual Turing conditions for that. But in fact, you can take lefty out completely. You can remove the inhibitor, and then at that point, if you kind of count up what's left, it turns out that this K equals 7 is the end of the simplified model. So in other words, the simplified model, you get a condition for bistability in a model that does not have lefty. And this was really this was very interesting to us for a bunch of reasons. One of them is that around about the time we were doing this work, a paper came out showing that in fact, kind of subject to a little bit of fiddling, you could in fact develop a left and a right-hand side, not very robustly, but without lefty, or with some fairly specific manipulations of lefty. So lefty seems to be there to impart additional robustness more than to actually develop the left and right side experimentally. And again, our work suggests a reason why that might be. But then, okay, so the big model, just numerically has bistability. So if you remember, the things that we put into the calculation of the coefficient of a fragment are cycles and edges. And if you have a model that has several conservation relations, your cycles are always going to be considerably smaller, and have lots of pieces that you're not using from the overall model. And so you can take edges that you weren't using before and add them to make a bigger fragment, right? So every time you add another edge, so you take something that's an edge out here that's not connected to any of this, and you just add it, and that gives you a fragment of the next order up, and you can keep doing that until you get to your end. So in other words, there are critical fragments of order n in the big model that includes lefty. They have this as their core, and then they have some other stuff added that just doesn't, kind of, once you're done calculating the coefficient, doesn't mess it up and still gives you a negative coefficient. And so if you've worked with larger models a little bit, you probably at some point noticed that if you get bistability, you can probably also find a range where you've got off bifurcations and vice versa. And this is part of the explanation, is that you can build, again, provided there's a few conservation relations, you can often build larger critical fragments out of smaller ones just by adding edges because of the way they enter into the calculation. Especially if you have lots of edges with a stoichiometric coefficient of 1, because they just contribute a factor of 1 to the whole thing. Okay. All right, so how did we actually find this critical fragment? Well, Maya and a couple of her collaborators some years ago wrote a piece of software called Gretelpi that does that. There's lots of things that Gretelpi, there's lots of additional requirement of Gretelpi that's required. I'll just put it that way. It's a bit awkward, but you can do some things with it that are really quite interesting in terms of starting to wrap your head around what's going on in a particular model. So so given that I had that we planned 2 lectures, I wanted to kind of keep this one not too horribly long, maybe give us some time for questions. So we're already at the conclusion. So the point of this particular method is that you find these critical fragments, which once you develop a bit of an eye for it, it's not actually crazy difficult to do. Those critical fragments, once you've found them, will let you say whether a mass action model is capable of bistability, Turing bifurcations, or positive feedback oscillations. And they'll also identify the part of the mechanism that's responsible for the behavior. On that point, actually, maybe, since I'm running fairly quick today, let me kind of run back here very quickly. So remember I was saying that there's more to the transcription factor than just pSMAD2 and SMAD4. So if I added other chemical species in here, so FOXH1 is one of the things, for example, that I could add in here, so that the complex of a pair of pSMAD2s and SMAD4 goes on to bind FOXH1 and some other things. So let's say I just added FOXH1. What would that do to this thing? What it would basically do would be it would add one more chemical species and one more reaction inserted into this part of the mechanism here. It would grow the mechanism by that much, right? And you would still have a critical fragment because you haven't changed the number of cycles, and you haven't changed you haven't thrown in any new stoichiometric coefficients that might mess up the calculation, because the stoichiometric coefficients would be 1 and they just appear as multiplicative factors. So what essentially what we're able to do is in some sense isolate the important interactions. So beyond just what part of the mechanism is responsible for the behavior, we can say what the important interactions are. And I'm going to come back to that in the next lecture, which I guess will be in February, because you can also go the other way and ask the question, what can I take out of this model without messing it up? So I'd like to thank you for your attention. My funding comes from the Natural Sciences and Engineering Research Council of Canada. They always want me to say that. Yeah, like I said, I've left a fair bit of time for discussion and questions.
So any question?
Thank you.
Marc, I have a question. Why can you give a very rough idea why your theory cannot apply to the non-mass Asian model?
So so we're using a bunch of tricks that Clark came up with first, which have to do with the fact that the derivative of a monomial is a particularly simple form. If you want to deal with non-mass action models, there are some methods that are kind of sit underneath what we're doing, and they're described in our first paper, that do something similar, but they work a little bit differently, and they're a little less clear in terms of identifying kind of circuits that are critical. What ends up happening for the non-mass action case with at least the methods that I'm familiar with is that you end up with kind of these skeletons, but you don't get a lot in the way of conditions as to kind of what the kinetics has to be in order to actually get say bistability or something, a saddle node bifurcation. Now, some people have done a lot more than we have along those lines. So René, what's René's last name? There's a Belgian group actually that did a bunch of work on this back in the 90s. And they went a little farther along those lines than we did for kind of general kinetics. But it's still kind of, the conditions you get they're not very sharp. So essentially what you end up with is, well, if you have this skeleton, then if you can find the right kinetics, then you might be able to get a saddle node bifurcation. But it's not very sharp. Now, one of the things I always tell people is, if you don't have mass action kinetics, of course, you can always fake it and create a mass action system that's equivalent, right? So if you've got a Michaelis-Menten type of term, just put back the reactant, the enzyme, the intermediate complex, and then the enzyme and product, then you're back to mass action, right? So it's I guess I like mass action because we can get pretty strong results. And if I don't have mass action, I just go backwards and recreate it, right? Same thing with Hill type kinetics, right? You can always convert that back into mass action because that's where it came from anyway. There's a handful of things that are not so easy, but generally speaking, you can just kind of work backwards to a mass action model and then work with that. But I admit, like, it would be nice to be able to work with non-mass action kinetics directly, right? That would be lovely if we could do that, and we can kind of, just not exactly with this critical fragment stuff.
Thank you.
Yes. I guess I should try to ask. I'm also a chemist, and I work in academia Sinica in Taipei now. And I just wanted to rethink, and because you start very slowly, explain things nicely, but all of a sudden I feel that the gradient of understanding and needed is slightly increased. Can we slightly go over that? Or actually, I understand the mathematical part actually really needs some time to digest. And before your next lecture, I think I'm willing to spend some time, but I cannot guarantee how much I will have time.
Of
But
course.
I guess some of my students who are online now, I mean, they are more than happy to. So, and they are shy, I'm sure. Okay. So maybe there is some material that you would refer us to, or you can try to go over it again, because I wanted to learn that how can you identify that critical network and why it is the network that guarantees something interesting is happening. You know, this is the only thing
Yeah,
I can
yeah, yeah.
understand now.
Yeah.
Okay.
Yeah.
Yeah.
So, yeah, I'll send Jicheng some references and he can share
Okay.
them. But so the way we do it is kind of twofold. So first of all, we know that we need subgraphs that have an odd number of positive cycles. So we start by, when we're doing
Oh,
smaller models, we start by specifically, we look for subgraphs with just one cycle. And quite
yes.
often those are not critical, but kind of while you're doing the little calculation of the coefficient, you realize, oh, if I had another cycle, it would work. And so a lot of the time
Oh,
what we end up doing is then we start asking, well, can I add, like one reaction to get another cycle
but
or something like that?
wait a minute. So when you say cycle, you don't have to follow the direction of the arrows. As long as they are geometrically a closed loop, then it is a cycle. You may have to go against the direction. Is that right?
Okay,
When you say negative, it was a little counterintuitive when you say there's a
yeah,
negative
yeah.
path or
So there are
something.
some things you can do and some things you can't. So maybe I should share my slide again and show you. All right. So let's see if I can find a nice example here. Because this cycle is really simple because it's positive the whole. Yeah, all these cycles are positive the whole way.
Okay, so positive meaning that we are actually going forward.
We're just following the arrows all the way around. Yeah.
Exactly. So that's good. That's good also. Yeah. So you said this is this. Yeah.
Yeah.
So you can find maybe like many cycles inside.
Yeah. So there's the big cycle that just goes all the way around the outside. There's a little cycle here.
Yes.
Right. So that's Michaelis-Menten. This cycle right here, right? So this reaction here is the reaction where the gene makes nodal, and this little thing is just representing the fact that the gene isn't consumed when it does that, right? And so there's a tiny little, positive cycle here. So there's actually, I think there's just the 3 cycles, but they don't appear in all the subgraphs. Okay. So when it, so the rule when you're, I should have I'll try next time to bring an example where there's a negative path or a couple of negative paths. The rule is that, let's say, so you start at a chemical species, and I always have to go with the direction of the arrow for my first step. And then when I get here, if it's a positive path, I'll be following an arrow again. But for a negative path, I would be going against an arrow at this point. So if there was another arrow pointing in here, I could follow it the other way. Okay. Now I get to this thing, I again have to follow an arrow for my first step in a path. So in a path, you always follow the first arrow, and then the first one, you either follow it or you go against it. Okay, and then you string these paths together to make a cycle. So that you can't follow you can't go against every arrow. You can only go against an arrow after you've already followed one. Does that make sense?
Yeah. And then this is the case with odd number of positive cycles. Is that?
Yeah, so so this it's been a while since I've drawn all the subgraphs for this thing, but this one has let's see. So there's one subgraph that's just the whole big cycle. And then there's a subgraph that involves this thing
Okay.
plus a bunch of
I
edges.
see. You need to think about the subgraphs and then
Yeah,
content.
it's a bit of work.
I see,
It's a
I
bit
see.
of work
I see.
to do this
So,
because
so
there's a
we
lot
would have to go through some exercise. Yes. Okay. We would have to do that. Yeah. Okay.
Yes,
Now
that's
I
right.
see.
Yeah. And
I can start to name my own problem set now. Okay.
there's a couple of older papers by Goldstein in Russia where they use slightly different terminology. It's a little confusing at times because they kind of changed. They changed. So we tried really hard to stick with the terminology established by Ivanova. Well, by Ivanova's translator, I suppose I should say. It was a Russian paper translated, right? And we tried to stick with that terminology, but then Goldstein translated it a different way, and sometimes you have to, it's a little confusing. But he has a whole bunch of examples, and we have some examples in our paper too.
Okay.
Yeah.
Okay. Yeah. Looking forward to that. Yeah.
Okay.
Very appreciating. So yeah, it sounds like a very very important thing that we can learn and then maybe try to understand more for the systems that we handle actually.
Well, in the interest,
I do also a bunch of work with biologists and try to see if we can say something, such that by building a model and then we can understand more.
Yeah. Yeah, and I mean, one of the things that I think, and one of the reasons I was really pleased to accept this invitation is, I think it'd be really interesting to compare kind of what we do and the kinds of results we obtain to what Zhiqiang gets with the theory that he's been working on with his colleagues. It strikes me too that some of the things I see in Zhiqiang's work look like the sorts of things you see in Feinberg's theory, because there's a whole other kind of what's it called? It's called reaction network theory developed by Feinberg that does a very similar. Yeah, it does a very similar thing.
Yeah.
Sorry.
We recently have you mean localized when you perturb it, and then the result of steady state. No, okay, no.
Yeah, no. Feinberg's thing works based on this quantity called the deficiency, and then there's a set of theorems, and the deficiency is essentially it's kind of a stoichiometric quantity that has to do with well, there's a few things that go into the deficiency, but one of them is kind of things like how many conservation relations there are, and then things like how many he calls them terminal linkage classes, so how many kind of dead ends there are in the mechanism where you just kind of sinks, if you will, that once things get in there they don't get out again.
Okay.
And you do this little bit of math, and then it gives you this deficiency. And then there's a set of theorems depending on what the deficiency is. There's a deficiency zero theorem that basically says if you get this, then you can't have any interesting behavior. There's a deficiency one theorem that says, well, deficiency one plus these other conditions rule out instabilities and so on. Yeah. So, and it seems to be there's a lot of connections. There's all these methods floating around. And there's got to be some deep connections between them, because ultimately they're all based on the same thing. They're based on analyzing the characteristic polynomial just in different ways.
Yeah, thank you.
You're welcome.
Yeah. I have a meeting coming up very soon, so I may disappear anytime now. So I see people are.
It's daytime where you are.
Yeah.
So just Professor Xu, I have sent you two reference from the Marc.
Oh.
Okay. I'll look up.
Thank you.
And there's a person whose hand is there. Atsushi?
Yeah.
Mochizuki-san, do you have any comment?
I have no, not comment. So yeah, thank you very much. So I'm Atsushi Mochizuki from Kyoto University, Japan.
Yes.
I'm
read your work.
Following the invitation by Professor Tai. Thank you very much for interesting talk. So giving strict criteria for the series of the bifurcation. But also, on the other hand, so in the field of the systems biology, so people there are many also naive and intuitive discussions about effect of the positive feedback loop. So people want to yes naively claim feedback likely to induce multi-stability. I want to know advantage of your method or the difference from such as naive discussions. For example, based on the naive discussions, they may found this system has positive feedback. So this system may have multi-stability, but also according to your strict criteria, it may be denied. Such clear difference maybe yes claiming the advantage of your method.
Yeah, exactly. So sometimes some of these things people say are not entirely wrong, but they're context dependent. So when you start to build the subgraphs, sometimes what happens is that you have something that by itself, if they wasn't connected to anything else, might generate an instability. But then because of the way it's connected to other things, you have to include additional subgraphs and they cancel out. And we see that all the time. Like you'll have an autocatalytic cycle, but because of the way it's connected into everything else, you can't just consider that autocatalytic cycle. It's because there's other things that end up in the subgraph. And so, yeah, I completely agree that, the kind of the rules of thumb of, look for this kind of thing, and that might give you, oscillations or bistability. They're kind of, they're the kind of the crudest kind of knowledge, and what we're trying to do is maybe give people a little more, right? The same way you are with the work you've done. Right?
Yeah. And yes, I thought that if you include some example which shows difference between your method, and their method. So in your presentations, it should be more appealing, I think.
Thank you. Yeah, you're right. I probably should find. We've seen lots over the years, and I don't normally take note because I always think, okay, that was not interesting because. But you're right. I mean, an example where an extra connection ruins the thing would be, I really should write one of those down and then have that.
Okay. Yeah. Thank you very much, Mark, and thank you very much for Sai-san, and thank you very much.
You're welcome. So, Professor Shi, would you like to have some comment? So, any further comment? Yeah.
Sorry. May I ask one? Can you hear me?
Yes.
Okay. My name is Takashi Okada. I'm one of the collaborators of
Yes. Yes, I recognize the name.
Nice to meet you. Thank you for great talk. I have a technical question. By positive feedback loop, do you mean positive cycle? Is that you defined, or?
Yeah. So, kind of the simplest case of a positive cycle is like we have in our lefty nodal model, where it's really you just follow the arrows all the way around, and that would be something that people would think about as positive feedback, right? So nodal, you follow it all the way around, and nodal makes more nodal, right? I mean, there are some more subtle cases of positive feedback where you have pairs of negative paths that cancel out in some sense, right?
Okay.
But the essence of positive feedback is that somehow, kind of some key species makes more of itself, and sometimes it's because of negative interactions rather than because of, kind of pairwise negative interactions rather than purely positive.
Okay. Okay, I see. So, and another question is that, so as you know, some reaction systems have conserved quantities as
Yes.
a linear. And so is there any difference in your method? So is there any difference in difficulty to study?
Yeah, no, not at all. So I guess I didn't mention this explicitly, so let me make it explicit now. So from the point of view of the graphical method, it doesn't make any difference.
Okay.
The place where it makes a difference, you need to know how many conservation relations there are, because that tells you kind of what the highest non-trivial coefficient of the characteristic polynomial is. So you need to know that to know kind of, you know, when to stop looking for critical fragments, right? There's no point. So if you have n independent chemical species, so in other words, you have, so like in the lefty nodal model, like I mentioned, there's like 18 species, 5 conservation relations. So the quantity we call n, which is the number of independent species, is 13. So there's no point looking for critical fragments bigger than 13 because that won't tell you anything, right? And critical fragments of order 13 specifically inform you about bistability, right? So we need to know that, but it doesn't actually make a difference to what you do in terms of the graphical analysis.
So so let me confirm. So can we use the same definition of the coefficient Ks for even for
Yeah. You have to number. So if you look in our papers, you have to number the characteristic polynomial terms a certain way in order for, you know, to have this nice correspondence. But yeah, it's really just an assignment of coefficients kind of issue.
I see.
Yeah.
Thank you very much. Yes, thank you for the
welcome. Yeah. And by the way, I very much enjoyed reading your joint paper.
Really?
That was I read the latest one. I haven't had time to read the other one yet, but very, very interesting. I think there's I look forward to, you know, maybe discussing this with you in more detail at some point in the future.
Yeah, thank you. Yeah, I'm glad to hear that. Yeah. Please ask us anything if you have. Yeah, if some, yeah.
I need to absorb it first, but yeah, I will.
Yeah. Okay. Thank you.
So, any comment? Okay. So the Marc will give 2 lectures, and the second lecture will be on February 1st at the Canada time, because our seminar is some kind of international.
Oh yes.
Basically, yesterday we made a mistake. And the second lecture is February 2nd in the Japanese time and the Taiwanese time. So for me, that's thanks to the Professor Roussel again.
Well, thank you for having me. It's been an absolute delight. And I look forward to giving you that second lecture in February.
Okay. So Marc, thank you very much again.
Thank you.
Okay. So see you on February 1st, Canada.
Yes.
Okay.
Yeah. Have a good day.
Okay. You too.
Bye.
Bye-bye.